So in this video, we're going to use area under a curve to calculate the volume of an oil leak. So the problem says at midnight, oil began leaking from a storage tank at a rate of 1 plus 0.7 T quarts per hour. By 4 a.m., how much oil had been lost from the storage tank? So I see this phrase here, quarts per hour, and right away I know that's a rate of change, which means I can use the net change theorem, which says that if I integrate a rate of change over a time interval, I get the total change that happened. So if I want to use quarts to represent quarts, I could say, hey, this is dq dt, the change in quarts with change in time is 1 plus 0.7 t is really 7/10 of a t if I want to write it as a fraction. Here is the rate of change function, which is always above the x-axis on the time interval from 0 to 4. And I'm going to work with the time interval from 0 to 4 because the oil leak started at midnight and I'm asked about how much oil had leaked by 4 a.m. So if midnight is time equals 0, then 4 a.m. is 4 hours later. So I'm working over that time interval from 0 to 4. And I pre-calculated this in GeoGebra. So GeoGebra told me the area under the curve, which represents the total oil that leaked, because the curve itself is the rate of change of the oil leak. It says 9.6, which is the same as 9 6/10, which is the same as 9 3/5 quarts. So when I work this through using calculus, I should get 9 3/5 quarts as the volume of oil that leaked from the tank over the time interval from 0 to 4 or midnight to 4 a.m. So the net change theorem tells me that if I want to know how much change occurred, or if I want to aggregate or total all of the change that happened over a given time interval, I'm going to take and integrate over that time interval. So I'm going to integrate from 0 to 4. And it says integrate your rate of change. My rate of change is a dq dt kind of thing, change in quarts over change in time. And of course I need to multiply that by dt, or change in time, to get change in quarts. I'm going to add up all the changes in quarts over that time interval to get the total number of quarts. I don't need to write this piece right here. I'm mostly doing this because I want you to see that what you get is a dq term, the change in quarts, which you're going to add up. Integral notation is just a Riemann sum as the number of estimating rectangles goes to infinity. So I'm going to integrate over the time interval from 0 to 4. My rate of change, dq dt, is 1 plus 7/10 of a t. I'm multiplying the rate of change, dq dt, times dt to get dq, the change in quarts. So we need an antiderivative. So an antiderivative of 1 is t, plus an antiderivative of 7/10 t is going to be 7/20 t squared. So if you differentiated, the 2 would come down and reduce the 20 back to the 10. That's the check on work. And we're integrating over the time interval from 0 to 4. So the fundamental theorem of calculus says find that antiderivative, then plug in your upper bound of integration everywhere you see your time variable, minus plug in your lower bound of integration, which we don't really need to do in this case because plugging in a 0 is going to zero out each of those terms. So this term here zeroes out, so I'm really left with 4 plus, and this is 7 over 20 times 4 squared, which is 4 times 4. So notice that we can do a little canceling right here. 4 goes into 25 times. So this is just 4 plus 7 times 1 times 4 is 28 over 5. And 28 over 5 is just 5 3/5. And then 4 plus 5 is 9, so we get 9 3/5 quarts leaked from the tank over the time interval from 0 to 4, or between midnight and 4 a.m. And that matches with what GeoGebra indicated I should get for the area under the curve.